In this video we're going to tackle a fairly tricky electricity problem. Pause the video now and try all parts of the question, bearing in mind that this isn't actually a question, they start here. Okay, let's start with the first part of the question. So it says calculate the diameter of the wire. Now what information is it given us? It's given us the resistivity of the wire, the resistance and the length. So hopefully that brings into mind the relationship between resistivity, resistance, area and length. We can of course rearrange this for area. Say the area is rho L over R, and area is of course pi r squared. So again we can rearrange this for radius and say it's the square root of rho L over R times pi. That is equal to the radius, and then if we want the diameter, it's of course 2 times this. So if we plug in all the numbers, we've got the resistivity, we've got the length, we know what pi is, we've got the resistance, you end up with the radius. Let's just type this in. So 9.7 times 10 to the minus 8 times by 0.5 over 0.07 times by pi. So we get the radius is 4.69 times 10 to the minus 4, and if we do 2 times the radius is the diameter, we get the diameter is 9.4 times 10 to the minus 4 meters. Part 3 says calculate the total resistance of the circuit. There is negligible internal resistance. So what have we got? We've got the current in the cell is 0.6 amps at 0.66 amps. So the current is measured here. So that's the total current in the whole circuit. So that's important. We know that the total potential difference is 1.5 volts, which means that the total resistance is going to be the total potential difference over the total current. So 1.5 over 0.66, which gives us 2.3 ohms. So it really is that simple because we know what the total potential difference is and the total current. So we may as well just say that all of this is one resistor. What is the resistance of that one resistor? In part 4, it now tells us the resistance of this one, which is 22 ohms, and it tells us the resistance of 3, which is 1.2 ohms, and it says calculate the current in R3. So if we can work out again the potential difference across R3, and we know its resistance, we can work out the current. So what potential difference is across this one? Well, it's 1.5 from here to here, so we need to use the potential divider formula to work out the potential difference across just 3. So what we're going to say is 1.2 over 1.2 plus 22 ohms times by our input potential difference will give us the potential difference of the 1.2 ohm resistor, which is 1.2 divided by 23.2 times by 1.5. So that gives us 0.078 volts. And then we can use this formula V over R, so 0.078 over 1.2. This gives our current 0.6 amps. Calculate the resistance of the probe when the resistance of R1 is 2.4 ohms. So this one becomes 2.4 ohms. We want the resistance of this probe. So we know that 0.6 amps is going this way, so what current is going through the top branch? Well, obviously the current in the top branch is 0.66 minus 0.6, which is 0.06 amps. Now we know that the potential difference across all of it divided by the total resistance across all of the top branch is going to give us this current. We know that the potential difference is 1.5, so 1.5 over 0.6 gives us the total resistance of the top branch, which is 2.5 ohms, and then the resistance of the probe is going to be 2.5 minus 2.4, which is 0.1 ohms. It's obviously the difference between the total resistance of the whole branch minus the resistance of this first resistor. Calculate the percentage change in the diameter of the probe when its resistance increases by 1.6 ohms. So if we write down our relationship between resistance and area, we can see that if the resistance increases, the area must decrease to make this work. So if the resistance increases by 1.6%, that's the same as saying 1.016 R is rho L over A. So what's going to happen? Well, the area will decrease by this amount, and the diameter is obviously related to area. So area is obviously pi d squared upon 4. So if the area decreases by this, then the diameter is going to increase by the square root. So if you plug all that into your calculator, so 1.016, so it should be the square root of 1.016, and then 1 divided by that answer, you end up with that the area has decreased to 99.2%, or by 0.8%. So what we're saying is the area has decreased by 1.6%, so the diameter decreases by the square root of that amount, and that is obviously the factor that we are looking at. You can't type in 1.6%, it doesn't work like that. If you type it in like this, it works. Now another way to do it would literally be to take this formula, or sorry, this formula here, and literally just plug in the numbers. You know what the resistance is, we worked it out, or sorry, we've been told, and then you could just literally calculate the new value of the resistance, and then rearrange for the diameter just like you've done here. Okay, question 7. So this is quite a tricky question. Voltmeters connected between points A and B, so between this point and this point, and R3 stays at 1.2 ohms. Explain without calculation why the reading on the voltmeter does not change when the cell in the circuit is replaced by another cell of the same EMF but a significant internal resistance. So what does this actually mean? A significant internal resistance means that there will be lost volts across the internal resistor, and then of course that means that the total current in the circuit will decrease because we've added more resistance into the whole circuit. We've effectively said there is another resistor here, so of course the current's going to decrease. But what hasn't changed? The ratio of resistances in this top section here hasn't changed. So the PD from A to B remains the same. Now that on its own is not particularly clear, I don't think. So although it says don't do a calculation, actually I think it is helpful to do a calculation to really illustrate this point. So with the values given in the question, we can work out what the potential difference is across each of the components. Now I'm going to use the potential divider formula like I used here, but I'm not going to write it out each time. I'm just going to tell you that the potential difference across this one will be 1.44 volts, across here is 0.06 volts, across this one 1.42 volts, and across here is 0.08 volts. So if we put a voltmeter across here, what are we reading? We're reading the difference between these two potential differences here. Because if you imagine your electron going round, you'd lose 1.44 here, you'd only lose 1.42 here. So there is a difference here of 0.02 volts. Now if we put an internal resistance in, this might drop to say 1.4 volts because there might be 0.1 volts lost across the internal resistor. So what are the new values of the potential differences? Well, we end up with 1.34 volts, and again I'm using the same potential divider equation, so I'm going to write it M. 0.056 across this one, 1.32 across this one, and 0.08 across this one. So again, what do we notice? There is the same difference between this one and this one, so from A to B. So the ratio of these resistors hasn't changed, so the ratio of potential differences across these two will change. Now importantly, this is true because actually the change in potential difference from here to here is not huge. I know it says significant internal resistance, but actually it's not significant enough to really change this ratio. If you imagined halving this potential difference, then yes, it would change, but we know it's a relatively small change. It's just enough, significant internal resistance is just enough of a change to reduce the percentage difference a bit. But like the question said, you don't need to do any of these calculations. Actually, this is enough to get the answer, but it does require quite a good understanding of this setup.